Hello, welcome back. Calculus 2. I got more to say about parametric equations. These are fun. Look at this one. X equals 3 cosine 2t and y equals 3 sine 2t. So that's a set of parametric equations. I could make a little chart and plot some points to try to see what it is. But maybe I'll just tell you what it is, or maybe you could guess what it is. You know, when x is cosine and y is sine, it makes you think of old trig. It might make you think of the unit circle when x was cosine and y was sine, except I've got a 3 here. Here's another way to think. You know, t is allowed, I told you t is allowed to be anything at once. But when it comes out of this cosine function, cosine spits out numbers between -1 and 1. Of course, if you're multiplied by 3, it spits out numbers between -3 and 3. So x lives between -3 and 3. Y lives between -3 and 3 because sine does the same thing. So anyway, the truth is, if you plug in a 0, you start at this point, and this is a circle. So this is good old circular motion, and it is moving this way. What is that? Counterclockwise. So this is, we say the orientation is always the direction of increasing t, so I put those little arrows on there. And so I'm just going to use the word counterclockwise here. This is circular, what we call circular motion, parametric equations. This is a classic circle, radius 3, centered at the origin, of course, centered at the origin, radius 3. It's interesting, like I said, it sort of starts here, although that word start is a little funny. It's circular motion. Where does it really start? T's allowed to be negative, T's allowed to be positive. So when I use the word start, it's a kind of a funny use of the word, but I'm implying that's when T is 0. But t is allowed to be before 0. T is allowed to be negative. But when t is 0, it's there, I think. Let me see. That's the cosine of 0 is 1 times, that's a 3, that's a 0. Yeah, it's at the point 3, 0 when t is 0. And then as t goes around, maybe to 2 pi, it comes back. But hang on a second. The period of this has been adjusted a little bit. You know, when you have a coefficient in front of t, the period is always, the old period for sine or cosine is 2 pi divided by that coefficient. So the period of this motion is pi. So without that coefficient of 2, I think it would have went around and it started and came back to where it started, done one cycle, one revolution. In 0 to 2 pi, its period would have been 2 pi. But with that 2 there, the period has been shortened to pi. So now it makes this trip, and it's back here when t is pi. Which, by the way, that means it's here when t is pi over 2. We have a shortened period, which means it's traveling faster. The period is the time it takes to do one oscillation, or one cycle, or one revolution in this case. You can use those words. And the time it takes has been shortened, which means it's traveling faster. We refer to that number as the angular velocity. The angular velocity. It's often referred to as omega. That number, that coefficient in front of t. Anyway, omega is 2. Okay, cool. What about this one? X equals 5. Well, oh, how about this? Hang on, I'm sorry. So what if I wanted to go the other way? What if I wanted to go the other way? And in a previous video, I said one way to reverse the motion is to change t to a negative t. So I guess I could do that. I could make that a negative t, and I think that would change the motion. I think it would go the other way. But one way I've memorized that to change the motion, I've just memorized this, is if you switch sine and cosine. So if x is sine and y is cosine, and then it starts in a different place too, by the way. I think it starts here, but then it goes clockwise. So then it's oriented clockwise. You can play around and investigate. One way to play is on your graphing calculator. You can go to Mode, and you can go to, instead of function mode, you can go to parametric mode. I don't have my graphing calculator with me, but you can go to parametric mode on a graphing calculator instead of function mode. And then when you type y equals, you don't see y equals, you see x1 of t equals y1 of t equals. And when you hit your variable button, it's now a t. So you can type in 3 cosine 2t, 3 sine 2t. You have to type in a set of parametric equations. They come as a set. And then you could graph this, you can adjust the window, you can adjust the t values, and so you can really play around. Playing with a graphing calculator is a good way to learn and play with parametric equations. You know, so I kind of convinced you that got a couple more things I want to say. I kind of convinced you this was a circle without saying too much. You know, one way to convince you is to eliminate the parameter. You know, we would eliminate the parameter by sort of solving for t and substituting, but that gets very complicated. Here, watch this. If I divide by the 3, so I really don't want to solve for t, but I want to solve for cosine of 2t, and then divide by the 3, y of 3 over 3 is sine of 2t. Now here's a true fact. You know this from trig. The cosine squared of an angle plus the sine squared of an angle is 1. That's the most fundamental identity there is in trig. Cosine squared plus sine squared is 1. So because that squared plus that squared is 1, then that squared plus that squared is 1. So using an identity, I've just eliminated the parameter. Cosine squared plus sine squared is 1, fundamental identity. So this squared plus this squared is a 1. And then I realized quickly that's x squared over 9, that's y squared over 9 equals 1. You know, maybe that looks like an ellipse if you studied section 10.1. An ellipse where the a and the b are both the same, that's a circle, that's not an ellipse. You multiply by 9 and we have x squared plus y squared equals 9. Classic circle centered at the origin, radius 3. When you eliminate the parameter, you have what's called the rectangular equation, which is the path, which, you know, proves to you that we're on this path. Now we're traveling on this path, you know, oriented counterclockwise in this case, and we're traveling rather speedy in this case. We've sped up, the angular velocity has increased, the period has shortened. So we have all those ideas. I like all those ideas. We're centered at the origin. I don't like to off-center these too much. If you added 4, that would shift all the x's over 4, and you'd be off-centered. Your x center would be over 4. You could add 5, and you've just moved it over 5, and over 4 and up 5. Your new center then is 4, 5, I guess. So you can off-center these things. I'm not too interested in that, but it might show up in some of your homework. Okay, cool. That was cool. So what if I want an ellipse? Remember, I used this, again, this is a little bit an error, but I said an ellipse was a circle with 2 radiuses, 2 radii. Well, that's kind of helpful here. All I got to do, you know, when those are 3s, the radius was 3. But if I make that a 7 and I make that a 2, all of a sudden I've got an ellipse. I've kind of got a circle with 2 different radius. And by the way, I got the same. I'll switch this up a little bit. Let's make this a 4t and a 4t. So what do I have here? This is all of a sudden an ellipse. Watch this. It's centered at the origin. The x's live between 7 and -7. If you think about the output of the cosine function, the x's live between 7 and -7. The y's live between 2 and -2. So that is a classic ellipse. It's centered at the origin, and I believe it's running counterclockwise. Again, I should put little arrows on there to indicate it's going counterclockwise. I said it's counterclockwise when x is cosine and y is sine. If you reverse those, then it's clockwise. To prove that, you just need to plot a couple points. Or again, if you play with your graphing calculator, you can watch it move. You can watch it, and it'll trace it out counterclockwise. It'll trace it out in the direction of increasing t. You know what's fun? Oh, by the way, what's the period of this one? The period is 2 pi over 4. So this one's really traveling faster. It's got a shortened period. That means it's traveling faster. That means it completes one full cycle. It starts here at 0. It completes one full cycle at pi over 2. So, you know, when is it here? Hang on. When is it here? Half of pi over 2, pi over 4. When is it here? Half of that, pi over 8. So, anyway. This is a fun one. Just for fun. If you are playing with a graphing calculator, this is not for the purposes of this, but for playing with a graphing calculator, it's fun to do this. Again, you can make up any number here, cosine or sine, put any number here, cosine or sine, but all of a sudden, make the angles different. Make this a 2t and then make this a 5t. Dude, that is wild. The x's live between -6 and 6. The y's live between -3 and 3. But the way it travels with those different angular velocities, it doesn't stay on the circle. It doesn't stay on the ellipse. It kind of does some of this kind of action. And it creates I don't know, it's way better than that. You should look at your graphing calculator. But it's a beautiful plaid pattern, perhaps. There's a beautiful symmetry in the motion. But that's what happens when you change these. I don't even know what to call it. It's just fun to play and explore a little bit. All right, I got a lot more to say about parametric equations, but this was important. Circular motion, elliptical motion, the period, the clockwise, the counterclockwise. So good luck. Please try some homework.